has a resonance. So that is then polar, which gives it the dipole-dipole. For some reason, the quietest is whenever there's only one element. Then it can only be one thing because there's nothing to take its electrons away from it, right? Remember, everything has dispersion. If it's polar, then it can also have dipole-dipole. And if it's polar with an H attached to an N, O, or F, then it can have hydrogen bonding. So those are the only things you have to figure out. Well, if one of the things that you have trouble with is figuring out if something's polar, then obviously you won't be able to do that. If one of the things you have trouble with is drawing out these structures, then obviously you won't have the ability to do that, right? So you've got to figure out where your weakness lies, because all of these things are required to sit there and look at something and go, oh, it's polar, so it's dipole-dipole. If you're like, how do they know it's dipole-dipole? Well, that probably means that you either can't draw the structure or you don't understand what polar actually means. This is polar because the electronegativity difference between oxygen and sulfur is bigger than 0.4. That means that there is a pool of these electrons in this bond down to this oxygen. That also means that there is a pool of the electrons of this bond down to this oxygen. There's a pool down here and a pool down here, but there's nothing pulling back this way. That's what polar means. Now we're starting to realize, hopefully, why polar matters. You know, that's why we learned that 2 units ago. Now we're actually using it. It matters because if there's dipole-dipole interactions, that affects the boiling point of something. That affects the freezing point of something. That affects a lot of different things, right? So keep that in mind. Well, let's jump down. Water versus bromine. Well, that is pretty easy. Even though bromine is going to have a huge amount of electrons, all it has is LD, London dispersion forces. Now here is the big question. Bromine and water are both liquids, right? Water has hydrogen bonding. And this is where it gets a little bit hard. Which one do you think has a greater boiling point, water or bromine?
Water.
Water does. Water still has a bigger one because of the hydrogen bonding. Bromine's is about 60 degrees Celsius. Yeah. What? Oh, it is. I don't think we have time today because of the shortened. Sorry, buddy. Now let's take a look. Let's go one more. Who's down below bromine?
Iodine?
Iodine. What do you think? What do you think's going on here? What state of matter is iodine?
Solid.
Solid.
So it has a IMF.
Yeah. But what type of forces do we have?
Just London dispersion, right?
We just have London dispersion, right? The melting point of iodine is 133.5. It's higher than the boiling point of water. Even though water has this hydrogen bonding thing, there are some, I mean, you just can't say, oh, this has hydrogen bonding, so it must be higher than this. The trend is, yes, this will have a higher boiling point than iodine, but you can see that there's a break in the trend. And, and that is when you get a lot more electrons.
Wait, Mr. Jackson?
Yeah.
Is it also because iodine's like a solid and water is a liquid?
Well, that's what I mean, though, right?
Yeah.
Iodine is a solid because of these forces of attraction it has on itself. The boiling point of iodine is about 185 degrees Celsius. Do you see what I'm saying? What is chlorine? Gas. Why is it a gas while iodine is, or while bromine is a liquid?
Less IMF.
Less IMF, less intermolecular forces, right? Why is iodine a solid while bromine is a liquid?
More
More
IMF.
electrons, more pulling itself together. Crystallization. All right, let's take a look here. Boom, 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 boom. We got that. I don't even know what this question means. So I just said which was stronger, intermolecular forces or covalent bonds? Covalent bonds are going to be stronger. Explain the reasons for the differences in boiling points between, and you can just look at these. I put around them like why. One is this is ionic bonding. Ionic bonding, if we take a look, I can't think of anything that's undergoing ionic bonding that's not a solid at room temperature, one. But take a look, this is halite. You guys know what halite is? Nope, not like quartz. More common, I think. Or maybe not. Anybody, halite.
Salt.
You got it. So, what I want to show, right? I think that that might be the best that I can show it on my screen. I don't even know if you can see it on your screen. So I'm going to show it from two different angles. You can see this way how it kind of goes, like it's broken right here, right? You can see the breaks maybe. And then whenever I put it this way, hopefully you can see what we call the cleavage. So the cleavage is where the points that it breaks at are. So this kind of looks like little weird thin stair steps. This is halide, so this is sodium chloride. If you were to lick this, it would taste salty. But this is in its condensed form. This is even more rocky than what we would call rock salt, right? This is yeah, this is just a block of salt. Yep. So if we take a look, this is a model that represents that block of salt in a sense. So which of these are the anions? If this is sodium chloride, green or blue is the chloride ion. Well, by definition, an ion does what? We're hurting. Friday. Friday, and there's a 2-hour delay day. What do ions do? What has happened to an ion?
They've lost or gained electrons.
Lost or gained electrons. What happened to the chloride ion?
They gained an electron.
You got it. So do they become bigger or smaller?
Bigger.
Bigger. What happened to the sodium ion?
They lost an electron, became smaller.
Became smaller. So which of these are the chloride ions?
The green.
Green is the chloride ion, right? Blue is the sodium ion. So if we take a look, if I try to pull this apart, you're going to see that cleavage that I'm talking about, because they're going to break apart in very set ways, right? So you can see that if I break it there, it has a certain pattern here and a certain pattern here. So if I were to take a hammer to that halite, we would see that same type of thing going on. Now, the last question of yesterday after the lesson was over was, what is ion dipole? And I thought to myself, well, maybe I just didn't describe it well enough, or maybe I should use this to show it. So here I've got water molecules, and we know that water molecules undergo hydrogen bonding. So imagine if we take this chunk of salt and we put it into water molecules. We'll take a look at what happens here. These water molecules will attract themselves to the particular ions. So if we take a look here, notice that the oxygens are bonding to sodium. if we get enough, we get what we call, well, they're not bonding in the sense, but they're interacting. This is an intermolecular force, right? They are ion dipole. There's a force that we would call this with the sodium. If enough of those get attached to that sodium, they can pull that off of there and then basically surround it. And we call that process solvation. Right? So that is now not a solid Na, but that is a Na aqueous. It's surrounded by the water molecules. Now I know I only have a certain number of water molecules. You have to imagine that all the space around here is also water, right? Well, let's take a look at the chlorine. Well, what's going to attack the chlorine? Since the chlorine is negative,
The hydrogen.
the hydrogens, this one must not have magnets in it. The hydrogens will attack themselves to the chlorine, the chloride ion. If enough get in on it and pull it away, then that will now become an ion. Right? So now, I'm sorry, an aqueous ion. So now that is aqueous as well. And here's the thing, remember when we talked about spectator ions last semester? Let's say that we react something else in here that becomes insoluble. It reacts with chlorine. Let's say it's lead. So this chlorine that's aqueous will be pulled out of here, but this will stay the same way it is. That's why it's a spectator. The chlorine reacts with lead to make an insoluble substance, but the sodium is going to sit in that solution. It's not going to filter out through through precipitation form. So that's just something to keep in mind. So hopefully that is a better explanation of what ion dipole is. All right. Down here, remember the highest boiling point. The highest boiling point will mean that it has the strongest intermolecular forces. So out of these three things, this one has hydrogen bonding. That's the strongest. Why is highest boiling point strongest? Right? We could even make a list if you have difficulty with this. Highest boiling point is the strongest intermolecular forces because they don't want to be separated. They want to keep holding on. It takes a lot more energy to get them. Lowest boiling point would be the what? Weakest. The lowest boiling point, they don't hold on to each other very well, so the boiling point doesn't have to be very high. How about highest freezing point? Do they need to hold on to each other very well, or does it matter for highest freezing point? Now here's the weird thing. The highest freezing point is also equal to the melting point. Freezing point and melting point are equal, right? So I would not think of this as highest freezing point in my mind. I would think of this as the highest melting point. Well, if you want to melt something, and it is hard to melt that, right? Which one has the highest melting point?
Probably NaCl since ionic.
You got it. NaCl would have the highest because it's ionic. HF, even though it has hydrogen bonding as well as the water, it is actually the lowest freezing point out of it. In reality, HF is a gas at room temperature. Water is a liquid at room temperature, and NaCl is a solid at room temperature, right? So definitely highest melting point is NaCl. Lowest vapor pressure. Vapor pressure is still a very hard one to get in our minds. Vapor pressure, if you have a very low vapor pressure, you have the strongest IMFs If you have a high vapor pressure, you have very weak IMFs. So this would be like London dispersion forces and nothing else. Stronger ones would be hydrogen bonding or something like that. But take a look, I2, all it has is London dispersion forces, right? All these other things, all they have is London dispersion forces. So I2 is the strongest interaction here. And again, it's pretty strong because of the number of electrons it has.
Wait, Mr. Jackson, I have a question.
Yeah.
Number 9, could you go over C and F? I don't know if I came a little late or if you didn't cover it.
C, PCl5, and PCl3. Which one has the highest boiling point? It looks
I thought it was PCl3 since it was polar.
PCl3 because it's polar. What is the electronegativity difference there? Hello? Hello? We lost him. The electronegativity difference there is PCl.
0.9.
0.9. So this has polar, this has dipole. And this has London dispersion forces. And that's all it has. This is one of those facts, just like that iodine. And that's why I wouldn't give you probably this in a testing situation, but we're still going to talk about it. If we were comparing these two, I would assume that you would say dipole. The problem is the sheer number of electrons that this ridiculous thing has gives it the highest boiling point.
But because it has so many more electrons, it kind of negates the fact that it has London dispersion.
You got it. Just like the iodine. Yep. And SO3 and SO2, I think both of them end up being having dipole. But again, since its London dispersion forces are higher, it also outbeats SO2 because of its number of electrons being higher. Its London dispersion forces are higher. So again, I wanted to put this on here so we could talk about that, but I would not probably have that as a test question unless it was exactly this thing.
Isn't SO3 non-polar?
What's the electronegativity difference on it?
Let's see. 1 second.
1, right?
Oh, I think I forgot the lone pair at the end. That's why.
There we go.
Okay, thank you.
Yep. All right. So for Monday, why don't you do this diagram here and 1 and 2. That should be enough. And we'll discuss that on Tuesday. On Monday, you will be watching a video because it's asynchronous over water. Nope. Today we're going to watch this video though. So just to give you an idea of these states of matter things, we have soda water. I want to optimize this video clip. Hopefully you guys in here can hear this okay. And hopefully it works at home. Let's take a look at the dispersion states of matter.
Think about a can of seltzer, an aluminum can filled with water and carbon dioxide. All the particles of matter in this can of seltzer are at the same temperature. They have the same average kinetic energy. Why then is the aluminum can a solid, the water a liquid, and the carbon dioxide a gas? Why isn't aluminum a liquid or CO2 a solid at room temperature? Well, let's look inside the can. According to kinetic molecular theory, the answer lies in the strength of attraction between particles of a substance. Let's take a closer look. A carbon dioxide molecule contains 1 carbon atom sharing electrons with 2 oxygen atoms. CO2 can exist as a nicely symmetrical molecule. However, its atoms are constantly moving. As the shape of CO2 changes, electrons are attracted towards whichever end has a greater positive charge. A dipole is created. As the shape of...
Now, take a look at this, because remember, this is not polar. So you might be looking at that and saying, wait, this is non-polar. But this is what dispersion forces look like. They're randomized dipole moments. They don't last very long. They're temporary. This one could easily switch in a second. The one next to it, like if there's another carbon dioxide near it, that can affect the dipole on this one.
CO2 continues to change, the location of the dipole also changes. This molecule is said to have a temporary dipole. A dipole on one molecule can induce a dipole on a neighboring molecule. This happens because the negative end of the dipole repels electrons in the adjacent molecule, causing them to shift position. The resulting force of attraction between two temporary dipoles is called, ironically, a dispersion force. This force is relatively small. Here's a model of condensed CO2. Some molecules have dipoles, others don't. Dispersion forces are present between some molecules. As energy is added to CO2, increased kinetic energy easily overcomes dispersion forces. Molecules move apart until, at room temperature, they exhibit the behavior of a gas. Water is also a molecular substance. One oxygen atom shares an electron with each of two hydrogens. Its shape, however, is not linear, but angular. This angular shape creates a dipole in the water molecules as electrons are strongly attracted to the highly electronegative oxygen nucleus. Water molecules have a permanent dipole. This model of an ice crystal shows how the polar molecules respond to a large number of attraction forces. These forces don't come and go as they do with temporary dipoles. Intermolecular forces in water are much stronger than those in carbon dioxide. Even when heated to room temperature, water molecules cannot completely overcome the attractive forces. They are held together sufficiently to exhibit the behavior of a liquid.
The last one here deals with a type of bonding that we just brush over. This is basically all we will touch of this. The concept is quite easy, but whenever we get into the parameters of it and everything, that's when it starts to get more difficult, I think, like trying to figure out where it all fits into this chemistry course this year. It may be something if you go on to advanced chemistry or something, it becomes more apparent. But this is metallic bonding.
The behavior of aluminum is governed by a different kind of force. Aluminum is a metal with an electron cloud of 13 electrons per atom. 3 of these electrons are available for bonding. You can think of each atom as a positive aluminum ion with 3 mobile valence electrons. Aluminum's properties are best explained by a model consisting of a crystalline array of positive ions engulfed in a sea of valence electrons. The particles in aluminum are atoms, but the forces that bind them together are forces of attraction between mobile electrons and fixed positive ions.
So you can see that these electrons are not sticking around the same nucleus, they're jumping from ion to ion. That's what gives metal these properties that are interesting. That's what gives metals the ability to be lustrous. That's known as the photoelectric effect. That's what allows them to get smashed versus the cleavage that we saw with the ionic compound. That allows them to be bended and be malleable because that crystalline structure can kind of almost bend and give way. It's also, since the electrons aren't standing in one place, that means that they can move, and that's what electricity is, moving electrons, right? So that's pretty important, but that's the idea.
Aluminum's 3 valence electrons per atom make these forces pretty strong. As energy is added to condensed aluminum, most of it is absorbed by increased ion vibration and electron motion. At room temperature, however, vibrations are not strong enough to break down the metal's crystal structure. This is why at room temperature, aluminum is a solid. In summary, the state in which a substance exists at room temperature depends upon the strength of the attraction between its particles. Can you use this principle to explain why almost all liquids and gases at room temperature are molecular substances?
Well, the thing is we know ionic compounds are not going to be liquid or gas at room temperature, basically, right? I can't think of any. We know that the metals aren't, except for mercury. But since in covalent compounds, which we studied the most with our bonding unit, you know that you can have something that's polar and something that's non-polar. And that's the biggest change in all of this. If it's polar, it's more likely to attract itself together. which would have a better chance of being a liquid than a gas at room temperature. If it's huge, we know it has a huge amount of dispersion forces, and that may allow it to be a solid at room temperature. That's what I got for today, guys. I did record this one as well. If you want a fuller version of today's